sorry for the goof up. I sent you the report probably. Yeah. So the subject name is Digital VSA Circuit, and the subject code is EC60204. It will be a 4 credit course every Monday, 10 to 11. Then every Wednesday 8 to 10. Today we are starting a bit late. Thursday, 10 to 11. Okay. So these digital VLSI circuits, what it will deal with, mainly first we'll start with the analysis process. Okay, I mean, it will start from the very basics. I mean, let me tell you, we'll take some historical perspective. Okay, try to find why it is important, and then by and by, you will start from the concept of threshold voltage. Why is it important in the context of digital VLSI circuits? And also, in fact, you'll be surprised that we'll start from the very basics of MOS device, so that people are coming from different backgrounds, so they can also cope up with the course. Okay, so don't worry. We'll go by and by. We'll explain everything in the class. And if anything is clear to you, please stop me then and there. Okay, also send me email. You know my email also. I'll be happy to answer. Okay, if I be of some use to you. So mainly we'll follow these two books, CMOS Digital Integrated Circuits, Analysis and Design by Kang and Ledlevisi. Okay, Tata McGraw book. The second one, Analysis and Design of Digital Integrated Circuits by the trio of authors, Hodges, Jackson, and Saleh. This is also a TMH book. Okay, and it deals mainly starting from the conventional device and going up to mainly the deep submicron device. Deep submicron means submicron, as you know, anything if the feature size is less than 1 micrometer, we call it to be a submicron device. Okay, and okay, let me see. Anything is wrong, Patrick? Sir, your screen is not shared.
Yes,
Okay,
sir,
but you can hear. But you can hear my voice. No problem. Huh? Okay, I'm sorry. Just see what happened. Let me see. Let me see. Yeah, now it is clear. Everyone? Hello, on.
Yes, sir. Now
yes,
it's
yes,
clear.
it's clear.
Okay. Now, why do you study about this field, digital VLSI circuits? In fact, the integration technology are progressing by leaps and bounds. Okay, and also the system design, that is also by the hierarchical approach. We can now design very complex uh, systems, and at several levels of abstraction we can look into this, and it is doable due to the presence of very due to the presence of different photolithographic techniques, and also integration technologies. So this has enabled the electronics industry to achieve a phenomenal growth. And in fact, in different domains, the progress has taken place. The use of integrated circuits, high performance computing. I mean, you got to know about digital signal processor. Okay, then telecommunications, mobile communication, consumer electronics, high definition television, to just to name a few. So use of integrated circuits is growing at a very fast pace, and the requirement of computational and information processing power of these applications is driving force. Why do you need such, and why so complicated design is required? The answer to this is that currently these the three domain performance computing, telecommunication, and consumer electronics, in these fields, different equipment and also products are required, electronic products, and they are built on very in computation intensive circuitry. Okay, and a lot of information processing is required. Be in the domain of video processing, particularly to name a few video processing. If you know that at any point of time, if you have to get uh, uh, you have to view a football match or a movie, okay, sci-fi movie, let's say. So at least 60 frames per second needs to be synced, okay, from the transmitting point over to the receiving point. So suppose you are hundreds of miles away, so the bandwidth that is required, that is huge, okay, but you cannot send it uh, by raw speed, okay. So you need to encode it, then decode it. So encoder and decoder circuitry for video processing. Just I'm taking this example to impress upon you the need of such high performance digital device. So that will require that some encoding is required and compression. This compression, my dear friends, need audio compression, video compression. This is highly important in the particular today's circuitry. Okay, so unless you know about, I mean, unless you can implement a very good compression algorithm, be it video compression, audio compression, everywhere, okay, multimedia compression. So the effect of this viewing of a what you call information intensive occurrences are not available at the receiver end. Okay, so huge computational power is required, and that you require the high power digital circuits. Then another thing is that monolithic integration of a large number of functions on a single chip. Now, you know from your several classes knowledge that we nowadays talk about SSR, that is small scale integration, medium scale integration, large scale integration, LSI, large scale integration. So that means we are now able to accommodate billions of transistors over a single silicon wafer. So that is possible, and what benefits it is, it gives you less area or volume, and therefore compactness. So over a chip size of say just 1 centimeter by let us say 1 centimeter by 2 centimeters, something like that. You can accommodate no less than say 10 to the power of 6 transistors, but in a proper manner with proper flow planning, with proper interconnection. So not only the logic computing elements, but the interconnection technology is equally important. Okay, and less area and volume means the power consumption will be less because signal has to travel over shorter distance, okay, compared to the conventional way. And also the resistive drop and capacity drop, all these things will just make a hint about where lies the benefits of the modern day circuit. Then less testing requirement at system level. You know why? Less testing requirements, if the system is spread around different geographical locations, then the testing equipment has to be taken at different locations. Okay, and then in-house testing has to be carried out. But if it is in a shorter space, and you can go by a methodical testing, okay, so the testing requirement also can be fine. In fact, it can be regularized. It can be done in a quick time, and also can be done very methodically. Then higher reliability due to improve on-chip interconnect. So shorter is the distance, better is the interconnect. But at the same point of time, the resolution should be very high. All this is done in a mechanical manner. And of course, higher speed because shorter distance for the signal to travel. And due to much reducer connection length and remarkable cost savings. But cost savings, you know that it has to be done in a foolproof manner. So for that, different algorithms are there which simplifies what we call the placement of chip, then routing, okay, and all that. So this will be discussed in, I think, there is a CAT course that we have got to take. And those who are taking. Now, again, we take recourse to some uh, what do you call, survey in the past. See, it started from 1980. I mean, at the beginning of VLSI era. And those who are interested in knowing the history of VLSI, I will urge you to study about. Probably you know about the book by Mead and Conway. I'll send you the name. Mead and Conway, the two authors in Caltech, that is California Institute of Technology. They wrote that on NMOS device, the distributed book is there. You just type in Google Mead, M-E, Carver Mead, and Lynn Conway, L-Y-N-N, Conway, C-O-N-W-A-Y. These two authors, Mead and Conway, they brought the concept of VLSI design to the classroom. Okay. Earlier, it was the sole prerogative of the industry. But if you read about the book, it is a very attractive. The design of the book is there. Please study. Just get a glance. Mead and Conway. Okay, two authors. M-E-A-D, Mead and Conway, C-O-W-A. Just you type these two authors, Mead and Conway, Introduction to NMOS VLSI Systems or something. Okay. And it was published in the 1980s, early 1980s. So they were professors. I don't know. They still may be there. So in Google, you get all the information. So then you know how the your design rules were framed. That means the circuitry, although we are sitting at our home or in the classroom, we can also design about the circuits. Okay, at least from the point of view, let us say floor planner. That when you build your house, okay, when your parents have built your own houses, you must have seen that you've gone to the planner and you have seen a very blue colored blueprint of the house. Okay, so different say ground floor, first floor, the rooms and all that. So right like that on a chip, where you are going to put the ALU, where you are going to put the shifter, then the memory. So you need to do a lot of floor planning and also interconnecting them with the system-wide signal, with the power, say 5-volt connection here, ground connection here, system-wide clock. If you are dealing with the synchronous sequential circuits, all that. Okay, so you need to do a lot of floor planning. So starting from 1980, you see the minimum feature size was 2 micrometers. Now, what do we mean by feature size? Feature size, can anybody tell me? Just let us be in a friendly mood. So, Ankit, Ankit, can you answer what do you mean by feature size?
Minimum channel length.
Very good. Yeah. So that means by feature size, normally we understand in the when we are down to the length of level of transistors. Okay, say MOS transistor, for example. So the minimum channel length, okay. Channel width. Okay, then other features are there like the depth of the diffusion in source drain island. But mostly when we talk about the feature size, okay, say and also Mead and Conway, they brought about the concept of lambda-based design, lambda-based tool. So two lambda, the Greek letter lambda, 2 lambda is the minimum size of the transistors in a particular technology. The 2 micrometer means the transistor length would be 2 micrometers. But relentless progress took place in the domain of fabrication technology. So currently, you are talking say 14 nanometer device, or even lower than 7 nanometer device. Okay, but it started in 1980s. It was said to, as I remember, maybe 2.5 micrometers, like 2.5 micrometers means 50 nanometers. So like that, okay, then 180 and so on. So gradually the progress took place, and it was expected based on Moore's law that the feature size will be 0.3 micrometer expected in 2000. But the actual progress overshot the expectation. So much was the progress in fabrication technology. Then by the time 2000 arrived, people were actually deriving say less than 0.3, maybe 0.2 or so. The actual development of technology exceeded the expectation. The minimum feature size of 0.2.5, that means 2.25 micrometer means 250 nanometer. Just historical, you need to remember. Just read as a story. 180 nanometer in 2001. So typical benchmark devices like 64 megabit dynamic RAM, Intel Pentium microprocessor, all of you have heard that nearly 3 billion transistors or more on a particular silicon chip. These were available in 1995, before the second millennium. Okay, then in 1997, he again further progress for gigabit DRAM and 150 nanometer semiconductor technology by NEC, Nippon Electronic Corporation. Now, you see here we are showing a particular trend. What is this trend? You see two lines, but with different slope. Here you see on the right side, right hand side, this has got a lower slope. Okay, say 1.25 per year. But this is a on your left. You have seen this is the trend showing how much the integration could be achieved on the domain of memory device. On your right, you see the processor. Now, the reason may be gauged. Why is it so? While you are building device, you see, we start from 4004 in 1970, then 8085, you have all known about this. So, I mean, in your in your microcontroller course, you have learned about 8085, 8048, 8051 microcontroller. So, I mean, by and by, more and more uh, concepts need to be incorporated. Like, say, for example, we went from this 8085 is a microprocessor.
Sir, hello.
Yes, yes, yes.
Sir, I think your voice is breaking. Can you reconfirm with someone else? Please, I am feeling so.
Yes, sir.
Okay. Yeah, yeah, I understand. Actually,
It
now,
is breaking continuously from the very beginning, I think.
okay, is it because of this device? Okay, let me see.
Might be because of the microphone you are using, sir.
Let me see. Okay, can you hear me clearly now?
Yes, sir, now it is clear.
Now it is clear.
Okay, I understand. That was maybe due to the device. Yeah. Okay, so what we have been discussing about, yeah. So see, so 8085, if you remember, this is a 8-bit microprocessor. What it has got? It has got a central processing unit. Then apart from that, you have got some what do you call micro program technology to if you write a program in assembly language that needs to be translated to binary streams. Okay, for that different things are there. Okay, and memory also is there. Memory means a very restricted amount of memory, like general purpose registers and so on. But when you are talking about microcontroller, the progress of microprocessor to microcontroller, you now you bring in the memory, the on-chip memory, like 8051. If you remember, it has got 1 kilobyte RAM and so on. Okay, so that if you try to accommodate memory within that, then you went to 68,000. This is Motorola processor, but 16-bit. Then you have got 32-bit. Okay, 68030, 8086, and so on. DEC Alpha, Pentium. Those are 64-bit machines. So as you increase the complexity, okay, of the machines, that is based on the motivation that we should perform different arithmetic operations also apart from binary operations. Okay, so if you need to accommodate different things like accommodate multiplier, then shifter, then whatnot, exponential operation, everything in a single chip, then the complexity will grow unimaginably. So it based on that
Excuse me.
yes, yes, yeah.
Excuse me, sir. This is coordinator Balu. Sir, sorry to interrupt, sir. Sir,
No
but 10
problem.
o'clock I have got a different class.
Oh yes, yes, yes. Yeah, dear friends, don't worry. Then what we do? I'm sorry for that. So we'll discuss tomorrow. Okay, 10 o'clock please. And now that the code is all of you have got the code, so I that teething problem will not be there. So tomorrow we shall start the class at 10 o'clock. Okay. Now we wish all of you a very happy new year. Okay, and please stay safe. Are some of you in the campus or most of you are at home? Hello.
Yes, sir. Some of them are in campus.
Okay, please stay safe because the corona is rising at a huge space, so we are all very frightened. Anyway, we have to go to the department, but due to the due to the infectability and transmissibility, we have to bear with the online class. Don't worry, I am sorry for today's goof up once again. I wish all of you a very happy, healthy stay wherever you are. Please stay secure, stay safe. Okay, so I think as Balakrishnan has to leave for class, and we have to be we have the time specified is 8 to 10. So today let us break. Tomorrow we shall join at 10 o'clock. Okay.
Okay.
Okay then.
Thank you, sir.
Thank you, dear friend. Thank you very much. Okay, stay fine.
Thank
Okay.
you, sir.
Thank
Thank
you,
you.
sir.